venga, venga, venga. Uh-huh. Good morning, everybody. I'm Madame Hartunian, and we begin the section on information theory and coding. We have 4 reports. Are everybody here? Reporters. Aram is here. And what about Iran presenters? They are not. Are they going to do online? You don't know? And Garik Adaman, is he? No? Because this person was always online, I think he will be connected. Well, then we can begin, and the first talk is mine, so I will go to the stage. Well, as you see, the title is some discussion on steganographic methods from the perspective of e-voting implementation. But before this discussion, I want to begin a little bit wider because we speak about the steganography methods for e-voting, and this research is conducted within the project on e-voting, on implementation of e-voting system. And our previous research, in our previous research, this project is going on already 2 years. First, on the first step, we investigated the existing systems all over the world to see which are the weaknesses of existing systems. We know that nowadays there are no 100% secure e-voting systems, and after that we suggested to use steganography for No. Well, we suggested to use steganography on this step. And I will just remind that the aim of steganography is to convey secret messages by embedding them within other data to hide the fact of communication. And we began our investigations from different steganographic systems from information theoretic point of view. The first model that you see is the model of is the Stego system with passive attacks. What does it mean in a few words? We have the legitimate users, Alice and Bob. You know that in cryptography, we call them Alice and Bob. And Alice must send some secret message to Bob through a public channel. And the steganography means that it will be embedded in another data, which we call a cover text. And the final text, which includes already the hidden message, is called a stego text. But Alice is not always active. It means that in some data, the message can be hidden. The attacker, adversary, why we call him passive? Because he cannot change anything in the sending message. There's read-only access to this public channel. But the task of if is to find out, is there a hidden message in this text? Is it a cover text or is it a stego text? We considered in this model the hypothesis testing. You know that hypothesis testing can have two types of errors, and these errors are connected. You cannot achieve a situation with both errors very small, and then the attacker must decide which is more important. And our result was to find the relationship on these error probabilities. Then we considered the next model with active attacks. Here, not only Alice, but also Eve can be active. Active or passive, not always active, but Eve has possibility to change or to send some fake information. And now the Bob's task is to decide whether the received data is a cover text or stego text. And after that, Bob must decide if this message is sent from Alice or from Eve. This means that, or for this purpose, we use the secret key for authentication. And we suggested to consider two-step hypothesis testing. This is what I'm speaking is about our previous research. That's why I'm not going to details, just reminding why we consider this steganography. So the first step, hypothesis testing, Bob must decide if the message is, if the data is cover text or stego text, or is there a hidden message? And if yes, then Bob goes to the second stage when he must decide, is it a legitimate source information or it is fake information from attacker. I will not go here to details. It is done by distributions. So the distributions of cover text, stego text are known, distribution of keys are known. And the difference is that Alice can encrypt according to joint distribution PMK, and Eve cannot do that. Here the distribution is independent. And if this research will be interesting, I can give the publication It is published last year in Universal Computer Science, a big paper with information, theoretical theorems and results. Here you see this model with active adversary, and secret key is added here for identification. And here you see that if have not only read access, but also write access. What is next? So, well, we suggest that we have a theoretical result, but which steganographic method to use for hiding information? And here we decided to classify all the algorithms to decide which one is useful from the e-voting system point of view. The first obvious classification is that all steganography algorithms can be divided into three classes. Pure, it means without any key. Well, it can work in some situation, but we understand that nowadays we must have higher level of security. Then with the key systems are the public, private key or secret key systems, the same as for cryptography. In steganography, we have the same situation. We can use the secret key systems where it is supposed that in advance one must exchange a secret key, which is not an easy task. Moreover, for users who don't know each other, or there are many users, so a more practical situation is with public key systems. I hope you are familiar with all this, and I go further. Then we are looking for existing methods in the literature. Here you can see it is the substitution method, transform domain, spread spectrum, statistical method, the distortion, cover generation. I will not explain all this because the time is short. It is in the paper in the proceedings. If it is interesting, it can be, you can find all the description of these methods. What is important that we come to discussion on all this, which is useful for e-voting systems. And I will stop here a little bit more detailed. What is going in e-voting systems? Assuming the voter data is securely entered into the storage server, it is then validated and cleared of the voter data so that the votes remain anonymous even to the counting server. We are then left with a database of votes consisting of voter keys, which are used for validation and cannot be used to obtain the voter's identity. And then vote itself, which is basically the candidate's index. So as in this situation, the data does not contain any media data. It is dangerous to use substitution techniques to hide the candidate index in the voter key, because this may corrupt the key and the counting server will be unable to verify the validity of the voter. Also, we cannot use any compression or other methods because it can distort the data. And we came to conclusion that the the best method is the statistical method on hypothesis testing. Here I will come to our conclusion that using statistical methods, we can considerably simplify the first step without the need to use a steganographic extraction algorithm to find out if the data is a valid vote or, for example, noise. A model based on the statistical method and hypothesis testing gives the best approximation of real-life implementation and is highly testable. The error probabilities can be calculated for both stages of data extraction, giving a clear understanding of the reliability of the method. I must point out that when on the first stage, the receiver do not use any extracting algorithm, he gains in time and in resources. So you don't need to use this algorithm to each received data to understand if there is a hidden message or not. So the hypothesis testing method gives this advantage. Furthermore, it is worth exploring the possibilities. This is our future thoughts on what to do then. Creating a hybrid method on top of a statistical one when building an e-voting system. The modular e-voting system model will allow the usage of several steganography methods for added security. That is all. Thank you for your attention. And if there are questions, I will be glad to answer. Yes.
I would say that we just admire your presentation. Thank you very much. And this is now the headache, another headache in securing and you did. Do you have any implementation in the real or tested system?
Not yet. It is just on this stage. After all the theoretical suggestions, the next step will be the implementation and testing. So we have 1 more year for this project to finalize our research.
Thank you. And do you have enough staff to do that? We may contribute.
Oh, this is the problem. I mean, well, we have the group who is involved in this research, but now we are on the stage where programming must be done. So we shall see.
Okay, we may be open for you to collaborate because that is very interesting. And then one more question concerning the privacy of the servers, because everything is stored on the server. How do you protect the servers? Do you have HSMs, hardware security modules that keep everything secret and do confidential computing? Thank you.
This is our first research, the first paper that was reported on the previous conference. The first step was to consider all the steps, what security issues we have in e-voting. You know, there are too much steps. So how to do that? The voter cannot vote 2 times. So nobody can see your vote, nobody can change, and so on. I cannot now bring all these steps, but many of these security issues are already solved. So there are many already implemented systems, e-voting systems. So we were looking, our research was on which part of this whole system is not very secure. So what to do there? That's why what is already existing, we don't work on that. So we take what is already done and just trying to add something where it is needed.
We wish you great success and looking forward to results. Thank you.
No other questions? Thank you. The next talk is improvement of growth rate bound of stock market with side information will be given by Isayan. Yes.
Hi, everyone. So the subject of our article is improvement of growth rate bound of stock market with side information. I'm Aram Yesayan. I am researcher of this institute, and I am head of chair of mathematics at French University. We did it with my colleague Artag Martirosyan. Artag Martirosyan was former researcher of this institute, and right now he is teaching financial mathematics at French University in Armenia. So before showing the main result, I want to do some introduction. What does it mean, stock market, portfolio, etc. So stock market is this collection of price relatives. So price relatives are random variables defined on the finite set X calligraphic X. So why we say price relatives, because this is ratio of the price of the end of the day to the price at the beginning of the day. So usually it's near to 1. So when xk, for example, equals to 1.03, it means that the KIF stock went up 3% that day. So we assume that probably distributions of price relative are unknown, but there are given different possible probability distributions for them. So if it is supposed that if the PD of random variable xk is GMK, so then for the stock market X, the joint PD, thereafter we will say that probability distribution is PD, is this one. So we denote M by M1, M2, etc. MK. So as I said, we don't know exact distribution of stock market. For that reason, we need to do test. For doing test, we need sample. So this is our sample, where Kn is a result of M realization of price relative NK. And in that case, the empirical PD will be this one. As I mentioned, we have to do hypothesis testing. So what does it mean, hypothesis? We know that hypothesis is an assumption that we have to accept or reject on the basis of the sample. So AGL is the hypothesis, characterizing the possible joint PD. So for doing this hypothesis testing, we define test Vn. So we define by division of sample space xkn into R key, this joint subset, because we have R to power key joint PD, probability distributions. So as I mentioned, we must make our decision on the base of the sample, so it is possible to have errors. And erroneous acceptance of hypothesis HL, provided that HM is true, is this one. And probability of rejection of hypothesis M when it is true equals to this summation. So we consider also reliability matrix. Reliabilities are defined as follow. So you can see here. And for example, when K equals to 4, reliability matrix has this 4. So And now we have to use logarithmically asymptotically optimal test. In brief, is a law. What does it mean, law? If for this matrix, if we have reliabilities, for example, for this matrix, we can give 3 elements of this matrix which satisfy some conditions, and the procedure will provide maximal value for other reliabilities. So as I said, here we have side information, and for that reason we have also conditional probability distribution. Gn given side information is defined by this, and here we have also error because the error probability of using unconditional PDGX instead of the conditional PDGX is defined by this, and so reliability is this upper limit. So now portfolio is this vector B1, B2, etc., BK. These are allocation of the wealth across. So the wealth relative is this product. So this maximum of growth rate. Growth rate is an expectation of logarithm S. So the maximum is called optimal growth rate, and the argument is called log optimal portfolio. So increase of growth rate is this one when instead of BM, instead we use incorrect portfolio BL. So our goal is to find new bound for this increase rate. So I want to mention that for this one, one interesting bound was found by Thomas Cover. The upper bound of this one was mutual information. So as I mentioned, the portfolio optimal portfolio theorems were deeply studied by Cover and his co-authors, and you can see the references. And law concept was studied by Professor Arutunian and his students. You can in 9/11 in important article of Alsvede Arutunian. Also, you can see the concept of law testing in this book. Arutunian, Yevgeny Arutunian, Mayram Arutunian, Ashot Arutunian. And first application of law hypothesis testing in portfolio theory is introduced in 2013 by Artag Martirosyan. Here we haven't side information, and Artag Martirosyan has found new bound, and this bound was forced in this article in 14 by using law existing theorem. So we need also this notion. What does it mean? The portfolios of maximal losses. The portfolio of maximal losses is this one, and other cases are the portfolios of non-maximal losses. So now the main result that we get bound for increased growth rate, which is this one. As I mentioned, the bound for this one was found by Thomas Cover, which was less than or equal to mutual information. Now this bound is few exact bound because this 1/n logarithm is smaller than 0. So we found new exact bound. And what does it mean? Mutual information. Mutual information is this one, and so we have corollaries. Corollary one is that we can, if n goes to infinity, so if we have big data, so we get this one, and this bound can be forced if we use law existing theorem. And as so that's all. And this article we dedicate to Professor Arutunian, and I suggest that we upload for Professor Arutunian. That's all.
Thank you for a nice report. Are there questions, please? How you are planning your future work? In which directions you can continue this research?
So, as I mentioned, there are many models proposed by Cover. So we want to take this models and show the application of Lao hypothesis testing in these models. Thank you. Thinking.
We don't have, do we have? Who is the, yes, here is, please. Yeah. Well, then the next speaker is Sadegzadeh, Mehdi Sadegzadeh. Yes, thank you, please. And the topic is preservation of people's privacy in social networks based on clustering-based honeybee optimization algorithm. Okay.
Presentation.
In the name of Allah, the Beneficent, the Merciful. Hello. Excuse me for some minute delay. The title of my presentation is Preservation of People's Privacy in Social Networks based on clustering-based honeybee optimization algorithm. I am Mehdi Sadegzadeh. from Islamic Azad University of Iran. In introduction, we know the ever-increasing expansion of the internet has led to the emergence of new subject of a study called social network on the internet, which is also called virtual or online communities. Considering that there is a lot of information about users' privacy in the data of social networks, it's necessary to make corrections on the real data in order to ensure the security of users' privacy. If the correction is too much, the usefulness of the social network data will decrease. We have lots of information. On the other hand, if the modification is not sufficient, the privacy information is not well protected. We need the balance between the privacy protection and utility. Some literature we have here, for example, the Liu and et al. And Liu and Terzi and Roma and Marquand and Ni et al. And Tianan et al. Because we have the short time, we has this literature. But the concept here that is in degree anonymization, reference Liu and et al., we have constraint a G star equal V and E star such that degree distribution is co-anonymous. This means we convert graph G to G star. So that in the figure you can see we have three nodes, one node degree 2 and 4 node degree 1. So that here degree 2, that is non-anonymous, that is ready for attack. But if we add the edge here, we have 3 degree with degree 2 and 2 node with degree 1. So that this is better. In the left figure, we have 1 degree anonymous because we have 1 degree of degree 2. And here we have 2 degree anonymous. We have 2 degree with degree 1, 2 node with degree 1, and 3 node with degree 2. So that we have 2 degree anonymous that is better from the left figure. So that we convert graph G to G star. Definition 1, a vector of integers V is anonymous if every distinct value Vi belong to V appears at least k times. Definition 2, a network G equal V and E is a k degree anonymous is the degree sequence of G is k anonymous. Our algorithm is based on a 2-step approach. This is the work of Liu. Degree sequence anonymization, we construct a k-degree anonymous sequence details equal D1, D2 until Dn tile from the degree sequence D equal D1, D2, Dn of the original network G using the definition 1. You can see this definition. We must reduce delta. Delta equals summation of I equal 1 to n, di tile minus di. That is absolute value. The lower the value of delta, the lower information loss of the anonymized network. And to graph modification, we build a new network, G tile equal V and E tile, where the degree sequence is equal to D tile by using basic edge modification operations. The operation allows us to modify the network structure according to anonymized degree sequence. As definition 2 state, the anonymized network G tile will be degree anonymous. So that in this definition, we only add or delete the edge and the number of vertices not changed. Here that is proposed method. In a start, we have 3 phases: pre-process, initial anonymization, and supplementary stage. In pre-processes, we input data set, build graph adjacency matrix, then compute degree of each node, make node degree list, and compute centrality degree of each node. And in the second phase, initial graph clustering using GraphQuad method, sort the list based on the degree and then centrality, and then select k-members clusters, then integrate non-k anonymous clusters. And in last phase, anonymization using honeybee optimization, and then apply final change on original graph. And here finish the algorithm. We have we use from two formula here. That is closeness centrality, that is equal 1 divided by summation of V and Vt for each t belong to V, and say degree, that is degree centrality, that is summation of Aij for all j. In short, in this section, the input is ready for clustering after we use from two formula. And first graph is built, then the degree of each node and the centrality of each degree of closeness are calculated. In the initial graph clustering, we use from graph cut clustering, considering the neighborhood and degree of each vertex. The graph cut clustering operation aims to transform the graph into clusters that have the lowest edge cutting cost and the highest profit in terms of the balance of the total degree of the verses into two parts that are created after cutting. In general, the resulting cluster will have the following characteristics. They are direct neighbors, that is complete graph, and created with the lowest cutting cost. There is the mass balance in the total degree of vertices and degree of closeness centrality. For a specific non-K anonymous clusters, K anonymization required the cluster have K vertices with the same degree. According to the result of clustering stage, there are three different situations for the clusters. If the cluster has at least K members and all vertices have the same degree, that is okay. The flag is set to true. If the cluster has at least K members, but not all vertices have the same degree, it gets a flag 1. Need to correction. And if the cluster less than K members, this cluster is merged with the closest cluster, because in each cluster we must have K nodes. Here, that is the flowchart of the honeybee algorithm used from this. And in completing kernels using the optimization algorithm, the output of previous step number of K unknown cluster and number of non-K unknown clusters. Completing kernels require that non-K anonymous cluster be anonymized by removing and adding K vertices and edges. For this task, to reach optimal condition, the optimization algorithm of the honeybee has been used. For anonymization, too many vertices and edges should be added or removed because the real data will be lost, and the amount of optimization anonymization should not be so low that the privacy of individual is compromised by adversary. For this purpose, the B-optimization algorithm used here for optimization. We have two parameters in the honeybee representation: number of vertices in the cluster and the degree of the vertex. They are considered as representation of the answer. The value change for the number of vertices between m divided by 2 and 2m, as well as the degree of vertex between 0 and largest degree of the vertex in the studied cluster. And here, that is, you can see the fitness function delta, that is summation of dCVI from I1 to 1 to n minus summation of I equal 1 to n, dC tile VI. This fitness function must be minimum. Excuse me. Apply final change to the original graph based on the result obtained in the previous step. The degree of each vertex is determined according to the vertex and degree of the original graph and the cluster size and degree calculated from the optimized algorithm. Change are made into graph as follows. If the degree are calculated for the vertex is lower than degree of the original graph, it must remove from its edge to reach the desired degree anonymity. If the degree calculated for a vertex is greater than the degree of original graph, an edge must be added to it, reach the desired degree of anonymity. If it is necessary to add vertices and edge, first a vertex is added to the number after the last number of vertices in the graph with 0 edge, and based on which vertex needs an edge is connected to the additional vertex with an edge. If there is a need to reduce an vertex and edge, first the edge related to vertex and removed, and then corresponding vertex is removed, and finally the number of the other vertices in the graph are shifted. For example, if 2 deleted, we have 3 converted to 2, 4 converted to 3, and so on. We have 2 data sets in this experiment, GRQC. You can see number of node edge. The CAGRQC, that is a data set for writers. For example, if a paper have 3 editors, we have a triangle that is connected to each other. And poolbook related to the USA collection. We have 3 metrics. Average path length, the distance between 2 vertices U and V, is the shortest path between U and V in the original graph. The social distance between all connected pairs in the graph is measured, but average path length and calculated with this formula. In this formula, the RP parameter details while all pairs of available vertices, and SVL U and V is the shortest path line between the vertices U and V. Second metric says that is average clustering coefficient. The clustering coefficient of a vertex is a ratio of possible triangle that exists through the vertex and is calculated through the following relationship with this formula. In this formula, the parameter T, the number of triangle through tau node U and degree of U is the degree of U. Then the average clustering coefficient of a graph is defined and the average clustering coefficient of all vertices. And third metric, that is transitivity. It is one of the transitivity clustering coefficient that define and measure the local loops near a vertex. In the other word, in the graph, the transitivity is calculated by the number of triangles and triple connection by this relation. In the simulation, you can see value of parameter, initial population, honeybee algorithm 50, representation string with length of subgraph node and degree for each node, number of iteration 50, lower limit 0, upper limit max degree of subgraph, number of employed bees 50, number of onlooker bees 25, and number of Scott bees 25. Considering that the main graph under investigation is a big data problem and trial and error, and this data is very time-consuming because we have, for example, in population at an age, remove this. For this reason, a real small data was used, a pullback data. The obtained parameter are the result of trial and error from this data set, considering that the problem could be solved with the default parameters of the proposed evolutionary method. The ratio of the population to the average error loss was used as efficiency creation. As a result, the smallest population that produced appropriate output was selected as the optimization population size. In the figure, you can see this. Here, if the population that is 50, that is good selection. If we have increased the population, that is better because modern data loss is decreased. But this needs more processing. So that the 50, that is good selection for population. In this figure, you can see APL, that is average path length. We can see the results show that the method worse than KDVM. Here, this method proposed, you can see, and worse than KDVM in a smaller K. But with the K increases, the proposed method, that is better result. For ACC, you can see the proposed method that is more anonymity than KDVM, that is reference 7. And that is better result. And for transitivity, we can see economization result of KDVM and vertex method is weaker than the proposed method. And here you can see result of information loss. That proposed method, that is less information loss. And finally, conclusion, in the proposed method, CAGRQC dataset was used as the main dataset and pullback dataset as auxiliary data. First data clustering was done in such a way that a less K vertices with the same degree and lower closest centrality values are placed in each cluster. And then the remaining cluster that have less that less than k vertices and have not yet reached k anonymity were anonymized by adding vertices and edges. By the evolutionary algorithm of artificial Bikernel optimization, removal and addition of vertex and edge was done optimally. The proposed method was evaluated with the three criteria, average path length, average clustering coefficient, and transitivity for k value from 250. Finally, the obtained numerical result was compared with the standard method presented in references, and the results showed that aligned with the anonymity of the social network graph data, the preservation of the usefulness in the proposed method is also greatly improved. Okay, thank you. Thank you for attention.
Thank you very much. Questions, please. Are there questions? If no, I have two questions. The first question is how you solve the bottleneck between privacy and utility. I mean, is it only experimentally shown, or you have some theory where you can find this bottleneck?
Yes, the problem that is we must use from the evolutionary algorithms such as honeybee, that is balancing in the first we say that is balancing between usefulness and anonymity. That is the main idea we go toward using the evolutionary algorithm. Here in the first I say, if the connection is too much, the usefulness of the social network data will decrease. Okay. Yes. We use from the fitness. We use from the fitness here. This is the fitness. Okay. The honeybee algorithm used from initial population. In initial population, we have a different degree for each node. Okay. For example, in the one individual of population, a node with degree 2, in the another a node degree 3. What individual in better? That is based on this fitness function. The honeybee search in the population and find the best solution, the best individual.
Well, you are based on this algorithm, yes, honeybee.
Honeybee, yes,
Yeah.
yes, the algorithm.
Why I ask this, because when you speak about information loss,
Yes.
the information theory metrics can
Yes.
work very good here, and rate distortion theory can
Yes.
give some theoretical results on this.
Okay.
And my second question is about a more global question. I mean, that in literature it is mentioned that k-anonymity is not enough for privacy. Do you familiar
Yes.
with differential privacy method?
We must shoot a balance between them. What is the meaning of privacy here? Okay, what is the meaning of privacy here? For example, in this graph, because we have, for example, papers, that is privacy in the graph. We have another paper is privacy in tables. In table, for example, we encrypt, for example, a major column that is important for me. For example, a student number not important, a student number. But for example, the age may be important because we have some report of this. But I don't authorize the, for example, report from here in this graph. Okay, we have one.
I know it is k-anonymity. I mean that it is not enough to guarantee the privacy. There are some publications on this. So I suggest you to consider the differential privacy more promisable method.
Yeah, I know. You can we can see, for example, another method for privacy that is not efficient. That is true. But here, for example, if you have converted graph, we don't have a degree, 1 degree, one node. One node with 1 degree. Here, the only node that degree 2, that is A. Okay. But here, that is, we have 3 node degree 2. That is more difficult. For example, that is A or B or C.
Okay, thank you.
Thank
Are there any other questions? Then thank you
Thank
once
you,
more.
thank you.
The next and the last talk in this section, given by Garika Damian, on the topic consistent clustering of Armagarch processes.
Hadi bakalım. View açayım mı inan? Açarsınız. Açalım. Ecco. Faccio che se io c'è stesso. Come per me stare. No, c'è. Adesso c'è un. Come stavo rubando questa. Gdzieś sarkę w случае она говорит. Jeszcze handla ja mówię.
Thank you. I want to present our work titled as Consistent Clustering of Armagarch Processes. Clustering in general is the task of machine learning to categorize similar observations without any supervision. And time series clustering is the task when the considerable objects are the time series samples. And this topic has a broad range of applications in different fields. The time series clustering approaches can be classified as feature-based, shape-based, and model-based. First two methods are considered as non-parametric versions, where we do not assume a specific distribution of underlying random processes. In the model-based approaches, we assume a specific probabilistic model under data generation process, and we use its assumption to build the clustering algorithms. But the main idea in all three methods is to define the distance measure on time series samples and use some suitable clustering algorithm. So one motivation is that we have here three observations of three IR1 models. First two are samples from the IR1 with the same coefficient, so it's the samples from the same model, and third one is a sample from another model. If we calculate all pairwise dissimilarity Euclidean distances between these time series, then we can see that we cannot distinguish between time series which are generated by the same model, but autocorrelation plots and the main characteristic of this first two time series are identical or nearly identical. So we need to define other dissimilarity measures to handle these situations. And another property that we are interested of clustering algorithms is called asymptotically consistency. We will define later it more strictly, but basically it's a property when you add more time series samples in a time domain, in a time axis, then we expect that the accuracy of clustering algorithm will be increasing. And here we have evaluation of different model-free non-parametric algorithms, and we can see that we don't have the clear asymptotically consistent pattern. So the Armagush process is defines here. So it's a random process that mean process is ARMA process, and the volatility epsilon t is the Garch PQ process. So we have X process satisfies these three equations. The problem of clustering. So we are observed n time series, and each time series may have arbitrary length, and we denote the length of xc by any. We assume that there are kappa unknown Armagush processes, and each xc is generated by one of the kappa unknown Armagush processes. Clustering function h is the same as clustering algorithm, takes the finite set of samples t and the target number of clusters kappa, and produce the partition C1 to C kappa, which is the partition of the index set. So it's our predicted clusters. More formally, the ground truth clusters, it's the partition G, ground truth cluster is the partition of index set, such that each xc in each cluster are generated by the same xk process. The consistency of the clustering function f, we say that a method is consistent for the set of sequences D if we can reconstruct the ground truth cluster G, and but if we denote by n the minimum number of each time samples in each time series, then f is called strongly asymptotically consistent in the offline sense if we can recover the ground truth clusters with one probability, and weakly asymptotically consistent if it probability tends to 1. So we can have by assuming that polynomials of Bz, roots of the polynomials Bz are outside of the unit circle, then we can represent arch part of the process by this infinite sum of the past epsilon squared t values, where epsilon c e coefficient are determined by these recursive equations for. And the analogical representation can be obtained by the ARMA part of the process. Here we have PBXT epsilon t for the ARMA part, and the P coefficient also determined by these recursive equations. So these two for the ARMA part, if we consider separately ARMA process and the GART process, these two infinite sequence completely determine the underlying model. Also, we assume, of course, a stationarity of the ARMA and GARCH part. So these two conditions are holding. We want to define metric on the ARMA-GARCH processes. Since we have two infinite sequences for each xt, yt ARMA-GARCH process, which are defining our random process, we define a metric on the U, which are the space of invertible Armagush processes, as follows. So it's the L2 norm on infinite P and C sequences. Here is U and V are positive constants. Usually they sum up to 1, and it's a mechanism to give more attention to mean process or the volatility process. So it's well-defined metric since this coefficient decreasing exponentially. So since we don't know the underlying process, we just observe the samples XC. We need to define some estimation of this theoretical D. Then if we denote by theta star the true parameter vectors of Armagush process, then we can, if the orders of these Armagush processes are known, so P star, etc., then we can use Gaussian quasi-log likelihood estimator of the theta. Then it's proven that under
regularity conditions. We have the strict convergence of the estimated parameters. If we don't know the orders of the process xt, then we need to somehow select these orders. This is done by adding some penalty constraint on the log likelihood, quotient log likelihood. We use the Bayesian information criteria, and it's proven that if we minimize these under M, which M is the set of candidate models, if the true model is in the candidate models, then you have the weak convergence. So the estimated parameters are weakly consistent. Having these results, we define the empirical distance between X1 and X2 samples, time series samples, where p hat and theta hats are calculated with the recursive equations on the estimated parameters in this case. And we define the distance empirical between time series and the process, true process, since we know if we know the P and C of the true process. So since these distances are the continuous function, from the parameters vectors, we can prove that these, if the orders are known, then the estimated distance is strictly consistent. And if the orders are not known, but we know the upper limits of the X and X1 and X2 processes, orders of these processes, we can use a big penalization, and we have the weak convergence. So the algorithm is very simple, which is used in many other papers. So it's just k farthest points initialization. So in the first step, we estimate all the models by if the orders known by log likelihood. If not, then big penalized log likelihood. Then we initialize k farthest points as a cluster centers, and then we assign remaining points to the closest centers. So for this algorithm, we have two results. If we assume that all underlying Armagh processes have the same orders, and we know that order, then if the target number of clusters is known, then algorithm 1 is strongly asymptotically consistent. And if we don't, this is more realistic theorem. If we don't know the orders, but we know some upper limits of the orders, then we have weak asymptotically consistency. And this is the some upper bound, lower bound, sorry, for the probability of reconstructing the ground truth clusters, which basically tends to 1 if minimum number of samples in each time series tends to infinity. So we also consider an alternative algorithm, which is the Key-Meadows algorithm, but we're using the distance metrics with our defined distance. So in this algorithm, proving the consistency for this algorithm is harder, but it works better on some practical applications. So two experiments maybe. We generate some random data set with 5 processes, setting Pmax, Qmax all equal to 3, and just to show the asymptotic properties of these two algorithms. So blue one and the orange, blue one is the algorithm 1, orange is the Key-Meadows algorithm, and green one is one non-parametric algorithm that we also evaluate other non-parametric algorithms, but this is like best. This is best one among. So we have the clear asymptotic patterns. We generate 600, 500, 1000, up to 2000 samples, and for evaluate clustering algorithms, we have clear asymptotic pattern. For general evaluation, we also have that algorithm 1 and Key-Meadows algorithm is better than K-means with dynamic time warping. K-means DTV is the notation for K-means dynamic time warping. But again, chemodoids outperforms both of them. Okay, and
Thank you. Are there questions, please? Yes.
Distance function cluster or the distance between the central cluster.
let me show you. Oh, no, we just here. So in the first step, when we estimate models and parameters, starting from here, we initialize cluster centers. In this case, we just pick the first point as a random point from our data set. The second point is the farthest point in our data set from the first cluster center. The second point is the farthest point between these two. So we initialize k farthest points in our data set. And then just for each item in our data set, we iterate over the clusters and the calculate closed cluster and assign it to this cluster.
Because the weakness of the game, okay,
Yes.
that is consider the distance between the member of each cluster and central cluster.
Yeah.
Okay? Don't consider the distance between the two central clusters that is much. Okay, that is the weakness of tables.
Okay.
If your algorithm consider the distance between the cluster that is maximized and linear distance being minimized or only consider one of this. Okay.
So this algorithm works only for the reason that if by our definition we define the time series in the sum cluster are the samples which are generated by the same model. If we have the consistency of the metric, we can show that in our definition, starting from the sum number of samples, samples in the same cluster are much closer than the samples from the different clusters. So for that reason, this algorithm works very well and we can prove the consistency. So it's only for the definition of our cluster. So we in some step, we have property so-called separability of the clusters. So we can strictly separate one cluster from other clusters. That's why this algorithm can be proven. But I say that in practical applications, maybe it's better to use chemodoids algorithm, which I think it's handling these situations. Yeah.
Thank you. Other questions, please? No questions. Thank you once more. That was our last talk. The section is closed. Thank you, everybody, for your attention and participation.
We have it.
А, ну тогда смотри, меня пес топлый ваный больше. Chicken, Ага. Видео на чат,